So I'm pretty excited to introduce the panelists that we have for this morning and afternoon sessions. First of all, we have Robert Cal, or Russell, Russell Cal. I'm just so focused on getting the last name right because I want to say Cahill and it's not. So Russell. Russell's here with PowerCorp. He's going to be focusing on the integration and kind of walking us through our first Wind Diesel 201 session. Following Russell, Steve Drouillet. Where are you, Steve? He'll be coming in after the break. And a couple, Tony Slayton Barker is going to be here after the event as well. So we'll kind of work our way through today. So Russell, to introduce Russell, he's been a member of the PowerCorp team since 2001, during which he's gained extensive knowledge in the renewable energy industry. Russell's current role has him overseeing the project management team, providing members with mentoring and leadership. Russell was heavily involved in the project management of multiple high-penetration wind diesel turnkey power stations that PowerCorp designed and constructed for Western Power and Verve Energy in Western Australia, and continues to be heavily involved in overseeing major projects not only in Australia, but around the world. So we're very fortunate to have these guys over here from Australia to lend their expertise to us today. So thank you for traveling so far. Thanks, Russell. I don't want my phone.
Okay. Thanks, Kat. Good morning, everybody. You'll have to bear with me with the accent. I don't think I can do too much about that. Hopefully today, the intention would be to make it a workshop. Bit of an interaction between you guys and myself. Hopefully I'll learn things as well along the way. That's certainly one of my goals today, is to learn things from you guys. Maybe someone's got some dying question that may come up through the slides. Put your hand up, let's see how we can go with that. Maybe other people in the room can help us get through some real life situations that you guys are thinking about or going through or have done. We certainly don't present to be the be all and end all. We're here to learn just as much as everybody else. So that said, we'll see if the technology is going to play the game. I'm impressed there's so many people here. I'm told that that's good snow out there. That I don't know. I'm a water skier. We don't have that much snow where I'm from in Australia, so I can water ski, but I'll give snow skiing a go later on in the week and probably be battered and bruised by the end of it. So let's see what happens here. Okay, so Wind Diesel 201, it's about understanding or getting an understanding or trying to get an understanding on wind diesel systems and what could you do, how could you do it. I can see Peter smiling. This is one of his slides that we share. So there's so many options. Well, maybe they're not all those options are applicable at your site, but there's certainly lots of options to consider when moving away or trying to supplement diesel or reduce your diesel consumption. And then there's always that underlying option that you're competing with, which is just to burn diesel. And that's a very real and cheap solution at the moment. So in Australia, we're paying about $1.50 for diesel for 1 litre. So if we keep that simple and make 1 litre 4 litres to the gallon, so you're looking at about $6 we're paying for a litre of diesel. I believe you guys are probably at about $3.70 at the Bowser. I think I saw in Anchorage, sounds something like that. Then delivered on site to your communities with some maybe government reductions in price, you're probably paying less than that on your sites. No, some people are shaking their head the other way, fine. And that's, I guess, if anyone in the room thinks that diesel prices are going to go down in the near future, that's awesome, and but I'm not sure that we all think that. No one really knows, and yeah, you'll see later on I've got a bit of a trend on oil prices, and we all know them, and it's what we're competing with, because at the end of the day, these solutions or these systems really need to have some sort of payback period, as well as the nice fact that it's probably better for the environment to make power out of renewables where you can. That's good, but there needs to be some sort of financial return possibly, or a benefit to the community in another way. So you've got all these solutions, potential solutions, therefore probably potential problems. And that being the case, then if you feed the customer too many different ideas, or you yourself are being bombarded with too many ideas and you are the customer or the potential customer, chances are you'll put it off till next year or until the next person in charge has to worry about it because you're only here for 10 years and then there'll be somebody else. Meanwhile, diesel prices will probably go up, possibly go up, I guess I should say. And interestingly enough, the price for the renewables could go up as well, or could come down in the case of solar. We've seen it come down in recent years. But that said, then you end up with this solution. Just keep burning diesel, and that's probably not the best solution for the long term, for the community, or for the environment. There's a very real risk of oil prices going through the roof. We see almost, it feels like almost on a weekly or daily basis, problems overseas with Egypt and now I think it's Saddam Hussein. Where's he from? Libya. All these oil-producing countries are having all these dramas, and so then all the future people on the oil market start jacking up the price or predicting the price to go up. And in Australia, I'm not sure about in America and up here, but in Australia, as soon as there's an article like that, all the bowser prices go up by 10 or 15 cents at the petrol stations where you're trying to buy diesel or petrol for your car, or gasoline as you guys call it. So that said, this is probably what a general diesel power station may look like, both the power station and the distribution system to the community. It may or may not have high voltage transmission lines, or it may or may not have a number of feeders. That's not really the issue here. Essentially, there's a central power station at the moment in a lot of these places that we're talking about. There's one place where the power comes from, and then everywhere else consumes it. That's sort of, I guess, how it is. And here we are in the room thinking, well, that's great, but we want to do crazy stuff. We want to put a wind turbine on that feeder. We want to put maybe a biodiesel or another type of generator over there, and maybe some type of generator over here, and we want power to flow in all funny sorts of directions, which the system originally wasn't designed for. So that is exciting, it's interesting, it comes with a whole lot of challenges, but it's certainly doable, and it's, in the end, that sort of solution is going to be a lot more cost effective if the renewable resources are there to run, and in a lot of regards more reliable due to no single point of failure anymore. So that's sort of what I guess we're going to try and talk through today. I look forward to you guys putting your hands up or having a bit of a conversation with me, if you can understand my accent. I don't know how you're going so far. Perfect, yeah, he's an Australian. I think there's one or two others in the room, so I hope everyone else can stick with me. What have we got? Okay, so yeah, what have we got? What are we going to talk about? So what I'd like to do is maybe go around the room and ask some probing questions to see if anyone's awake. Where do you guys come from? What sort of skills and backgrounds and interests we have in the room. Then I'd like to go through this diesel power station design. From our point of view, in our experience, it seems to make no sense to talk about the renewables until you have a pretty good grasp on what the diesel is that's either already there or about to be built, if it's a greenfield site, for example. So that's great talking about the renewables because that's the fun part, but until you understand what's existing or what you're integrating with or what the base load power station is going to look like, it's almost the horse before the cart before the horse. So then, of course, we will talk about wind in this case. We've done other types of renewables as well. This is a wind diesel conference, but the same rules apply. You know, what are the tricks? What do we know about them? What are the hazards or the things to look out for when integrating these sort of things? And then the confusion I'd suggest about why do you need to integrate some sort of fancy thing called storage or stability or any other trendy words that are being used around the place? What's that about? Can't I just put a wind turbine in next to the power station or down the road and get things going? And I'll try and shed a bit of light on that, and I'd encourage you guys to ask questions certainly in that area. With a bit of luck, it worked this morning when I tried it. We might try and dial into a power station that we built last year and the year before, which is in Antarctica, down the other end of the planet, and have a look at it up there and see what that all means, and in context of what we've talked about in the morning. Hopefully. It's got to go through the internet, back to Australia and then down to Antarctica. So there's a chance it won't work. And then, yeah, what else could we do? Once having done all that, we've done the diesel power station, we've put the renewables in, we've tuned it up. What else could we do to the place? What could we do to make things better, save a bit more fuel? So, yeah. Who's here? I'm here. That's about me. I started in this industry in power generation in particular. I actually did my time as an apprentice electrician, and then went on to a university and did the engineering. Worked for a couple of different companies, all based in Darwin in Australia, which is up the top of Australia in the tropical part. I'll need someone to convert for me, but our temperatures average, well, our temperatures probably range between 30 and 33 degrees Celsius every day, day in, day out. Some days it rains, other days it doesn't, but the temperature rarely changes. So I don't know how that converts to Fahrenheit, probably 100. There you go. It's exactly like here. Although you guys have got all this white dirt. We don't have white dirt, ours is red or brown. So yeah, nice part of the world for that type of an environment. Luckily enough for me, I've been able to travel a lot with PowerCorp and the previous employers, doing this sort of thing, looking at lots of different power stations, talking to lots of different people, learning of all these different people around the world, how they do it, what works for them, what doesn't work for them. It's been an exciting career. Spent some time in Alaska and recently in Canada as well, so learning a bit about this northern hemisphere type of system and the idiosyncrasies that you guys have up here. Interestingly enough, the systems that we do in Australia are very similar to those, especially of Alaska, where they're far away, remote, often isolated, not necessarily by snow or ice, more like floods or cyclones. We rip the roads to pieces. Indigenous people living in these remote places, all the issues that are around them. It's a government-funded environment, a lot of it, and then there's issues with that and the politics and the bureaucracy that goes with that. So from my experience in talking to people in Alaska, there's some similarities there, there's some differences. There's a fixed price tariff in these communities in Australia, so the consumers are paying the same rate as those in the capital cities. So there's no, it's a huge loss-making business for the utility who's funding these systems. So for them, if there's an ability to reduce their fuel consumption, they're interested. I don't believe that's the case here. I think that the communities here all work out their own tariffs. I think something to that effect, or they have different arrangements up here. You know, that's an interesting driver. We often try to look at the projects or the opportunities that come along, or consultancies that people want us to do, and then we can say, well, this clearly isn't going to be a positive net present value. This won't pay for itself inside of the life of the equipment that we would like to install. And often that's not necessarily a problem for the consumer or the customer, the utility. They are just looking to save a huge amount of fuel during that period of time because they believe fuel prices may go up, these sort of things. So apparently that's all about me. I might have drifted there a little bit. I guess I want to ask people, what type of people are in the room? I've got a few things here to remind me or prompt me to ask you guys. Do we have like power station operators or owners here, those sort of people, are they in the room? No, that's okay. We all have to do it. Oh, there's a couple of there. Half, sometimes. Yeah. So sometimes you're there, over here, yep. So, I mean, these guys are the guys on the ground when we leave. They're still there operating the power station or living nearby or having to support the power station maybe from another location. Arguably your best friend, or the person you want to keep as your best friend when you go to these sites. People from the diesel side of this industry, have we got diesel companies represented? There's a lady there. That's just as much a part of the wind diesel system as the wind is, or the renewable energy, whatever it is, without a diesel system that you understand very well and can rely on, and beep beep, that's okay, yeah, then it all falls over. So, and the renewable isn't going to be there all day, every day. It'll come and go. I believe up here you have quite strong wind resources, so, you know, possibly stronger than other places. We've got sites in Australia where they have very windy months of the year and they're not so windy months of the year, so the diesel power station does work quite hard during those periods of time. Likewise, we've done some solar systems. You'll hear from my colleague, I think tomorrow. He'll talk about a solar system we did, high penetration solar diesel. Clearly at night time, solar's not really happening that much in Australia anyway, not sure about up here. Yeah, so those sort of things are just important. The diesel power station needs to be well understood and reliable, and there's an integration with it to understand how it works. Arguably quite an important part of the system. People here from wind turbine backgrounds, consultancies, companies, a couple of people. Obviously that's what we're here talking about. They're critical, they're all different. Every brand has different idiosyncrasies, different ways they do their blades, different ways they control themselves. From my point of view, we try not to get too involved in how the wind turbine itself works. We just want to hook up the cables at the bottom and maybe give it some control set points, and then it's got to do its job. A bit like the diesels, we don't want to know how the pistons go up and down and the fuel injection systems and those sort of things. That's their world. And but that said, you need to have a broad understanding of how that particular brand of machine that you've chosen or you have at your site works. You know, they all have great features and they all have not so great features depending on the environment and how they were assembled, what type of machines they are. Storage or stability type people. Yep, one guy here from Beacon Power, so they're flywheel people as well. We do have a flywheel product. I'm not going to talk too much about that today unless you want me to. The storage slash stability was the section I had earlier called confusion. I'll try and talk about it and either confuse you more or less. Let me know which way I'm going with that. What else have I got? Consultants, people who help us work out how to do these things. Yep, a couple of those sort of people in the room. I mean, you guys are working these things out with your experience from other sites. I think it's super valuable to be up to date and learn about the latest things. So I'm glad people are here, and I'd be keen to talk to those sort of people, or all those sorts of people as well, to learn what other companies are doing, what tricks are working, what's not working. If there's things that we've done that haven't worked, we'll certainly let you know about them, and there's probably a few. Was there anyone else who wants to take my position up here? Didn't think there'd be any hands up for that one. So yeah, there's other people in the room clearly with either interests or some sort of background or in this wind diesel system. Feel free to put your hands up, introduce yourself, let us know what you're interested in or your questions might be. Like I said, it is a workshop. We do want to encourage people to interact. My voice will get a bit boring? No, a bit monotonous after a while, I'm sure. So, especially with that strange accent. So what I'd like to do is grab a drink of water and just start to talk about what would necessarily normally make up this diesel power plant, because we've learnt that without the diesel being sorted out first, it's no good really talking about the renewable bits through. So I'll walk you through that to start, and just give me a moment. So diesels are really easy because they're all the same, apparently, or we'd like to think. But they're not, unfortunately, and there's many different types, and then there's many different types of way they behave. There's, you know, the turbocharged machines, the non-turbocharged, mechanically governed, electromechanically governed, electronic machines, and many others, I'm sure. Now, I think in that order, we're probably looking at a lot more machines, electronic fuel injected these days. But that said, if we're at a site or we're talking to people who have older equipment, then they may be running older type of governing systems. And generally speaking, the older the governing system, the more difficult it is to just throw a wind turbine in and push that power station around. The benefit of having these fancier, more computer-based electronic fuel injection engines is they are able to react much quicker to either surges from the wind turbine or sudden drops in energy from the wind turbine, which means the diesels are there to pick it up or back off accordingly. So that's pretty important and very important to understand early on what the machines are, and there may be upgrades required. There's all the different speeds the diesels do. Clearly this is inertia, and also the capabilities of what the manufacturers say the machines will do, and then what you say the machines can do, and what the operator has seen the machine do. So there's 3 or 4 very different points of view there. It's always a good conversation to have. And then there's the different types of fuels which inherently either complement or cause the machine not to behave as well as we'd like. I guess it's characteristic of what we're trying to do here is put renewables into a diesel system, assuming there's already one existing. However, the consumers at the end of the day, whilst they feel warm and fuzzy and it's nice to have that renewable thing out there that's apparently making my power greener and the community is saving money, they're not interested in having lots of blackouts. That's not going to cut it for them, and very quickly there'll be a little riot and the machine will be burnt to the ground and the diesels will be back. So we need to understand, and we need to get buy-in from the consumers, and we need to make these systems reliable, I believe, and I think these days the technology is there to do it. Maybe in early days people were prepared to tolerate occasional blackouts, but I think less and less. The consumers, even in remote locations, are still running the big plasma screen and the DVD player and bits and pieces, and they're not interested in seeing power surges and blowing up that equipment, or blackouts, meaning they can't watch the latest ice hockey game, for example. So those sort of things are super important to understand from a diesel point of view. I'm not sure if anyone else has other big diesel comments to make there. I'd encourage you to put up your hands. I'm seeing that happening all around the room. I'll get you to just do one at a time. That was a joke. Okay, so then goes with the control system that may or may not already be there. We've seen, travelling throughout the world, lots of types of control systems, and the manual operated control systems, some of them are pretty good, pretty well organised, next to no blackouts. Maybe they're not as fuel efficient as an automatic system, but maybe they're employing some local people, and it's part of the local economy to have half a dozen guys employed at the power station, either running it or operating, maintaining it, keeping it clean, keeping the servicing happening. And that's an interesting area to negotiate with, and it's not necessarily the case that those people would lose their jobs when the big wind turbine or the big renewable resource gets installed. There's still a servicing role that needs to happen there. There's a training role. There's even a community buy-in type role to make sure that the community supports what you're doing. There's other types of control systems. There's like a hybrid version there where it may be semi-automatic or semi-manually controlled, and of course then there's automatic control systems you see these days that take care of switching engines on and off and all that sort of stuff. That said, there's a few fundamentals there that if the batteries go flat, for example, in a blackout, the engines don't just start themselves. The place will be dark until a human interacts. So there's a lot to be understood of either what's there or what's intended to be put there. And often it's an area that's not well understood, or it's old. There's probably a couple of people in the room that could nod their heads towards these last two and say, yeah, it's great. We've got a control system that was installed 10 or 15 years ago and works really well. We just want you to add the wind bit on the side, and that'd be great. Only problem is, of course, the company that did it for you is long since gone, or you don't have access to the software that they installed, or the hardware that it's mounted on is no longer available from the manufacturer. And then you find yourself in a situation where you're trying to integrate old with new or not, all new, rip the old out. Why'd you do that? It was working perfectly fine. And there's that whole communication that needs to take place to try and understand what is the best solution, most cost effective, as well as performance-wise for the future. It's all well and good to save the customer money by integrating with their old equipment today, but if the old equipment starts to fail in the next year, 2, 3, 4, then the system, and you were the last one to touch it, is not reliable. Doesn't look so good, even though in fact it may turn out that your equipment is still working fine. It's the older system starting to fail. So it's a tricky one to understand. And then of course that all of these systems operate in super unbelievably amount of different ways. There's a lot of people doing ways differently, and they all generally work the same, that the engines come and go matching to the load. Some have different control philosophies that say you need to have this many engines on in this time. We want to run the small ones, then we want to run the medium one, then the big one, or we want to run the big one all the time because he's our favourite. We want to run the yellow one because we like yellow. You know, there's all those sort of things that you need to understand and work with within the control system. So it's not as easy as you'd like to think. And generally they look a bit like this. A bit like that picture I showed earlier, where it's, if there is a control system of sorts, it's generally controlled by some sort of master over some sort of wires, whatever communications may be existing, talking to the generators, and then something talking to the feeders sometimes. That's possibly not necessarily always the case. So this magic box here does the decisions and works out how things go, which is great, and that historically has worked well for a long period of time. Only main problem with that is that it's a single point of failure. So if that box decides to lose its brain, then the system is no longer operating as an automatic system, and blackouts or less fuel efficient solutions are running at the power station. So I guess it needs to be understood and compared to whether or not the system may be now one of these newer ways people are starting to think about things where everything's decentralised and they all talk to one another individually. So there isn't a single point of failure. It's quite interesting getting to understand these types of systems. And interestingly enough, I've got a slide next that talks about the comparison of the two. But essentially, if this device here, with its little brain, wants to do more or less work, or let the others know that he's, well, I won't start with that. I'll start with the diesel. This diesel's got an engine oil pressure problem. Look guys, I'm low on oil pressure. I want to get off. I've got to go. He just puts that message out there. Everybody else can understand it and react accordingly against their known set of parameters, that how that will affect them. So these guys, maybe they weren't on. So the next one in the priority that was preset by a human at some point in time says, oh, okay, I'm in. I'll get in there and help you out. Maybe the renewables are able to provide more energy during that period of time while there's a changeover. Maybe the grid stabilising system's able to help out if it actually goes offline instantaneously and there's a failure there. And that type of control was certainly done under the other method where there's a single point of control. But this distributed control structure is starting to become more and more apparent. It's come out of the motor vehicle factories, production lines, where historically there was one major PLC or big master computer or huge amount of relays somewhere in some panel somewhere. And now they apparently have distributed the smarts throughout the factory so that if any one point of equipment either fails or power trips off to a circuit breaker somewhere or something happens, then the whole system doesn't necessarily stop. It may have to if it's a critical point in the production line, but it may not necessarily have to stop. The system could keep going, and that's the case with these distributed systems there. So the two systems there, I believe everyone will get copies of the slides, so I won't read them to you, but there's quite a few interesting different ways of doing things with these centralised versus distributed control systems. So when we turn up, or you guys are looking at integrating a renewable or whatever you're trying to do, even if you're just trying to put in another diesel engine, need to understand how that existing control system works, where you're going to integrate, how's that going to work, is the system easily upgradable, can you just plug in another device onto their data network, or is it the case there's a lot of hard wiring still going on? So these sort of systems are interesting and challenging to work with, but once understood, I think the decentralised structure gives the client a little bit higher levels of confidence, maybe, a bit more redundancy, quite a lot of levels of redundancy before the power should fail or blackout. And yeah, quite a lot with the technology now that's there with the communications, that's where these systems are starting to come in their own. So I guess we've got our diesels sorted out, we know what brand they are, what colour they are, these sort of things. We then need to know how the machine behaves. It's all well and good to download the manufacturer's specification and performance curves and all these things, but if it's an older machine and they're not always brand new when you turn up, or if it's in an environment that's got temperature limitations, or there's other limitations being applied to it, whatever they might be, then generally speaking, the machines actually need to be tested. The actual machines you're going to work with need to be tested to see how they behave. You know, generally that's done with just a load bank or some sort of form of metering equipment that takes place during large loads, which would simulate the wind turbine being there doing a great job and suddenly disappearing, and the diesel is left to carry it. How did the diesel behave in that situation? So that would, what we would term as step load response, I think that's a phrase we might have dreamed up inside our building. And likewise, how they reject energy. So if suddenly the wind turbine comes back online and steals 3/4 of the energy from the grid, how do the diesels react to that? Do they go out in overspeed, and because suddenly they've got no load on them, they all speed up and then they trip out on over frequency alarms or all sorts of things. So the only way to test these things is, well, the only way to understand or know these things is to test them, I guess. And then how do they behave in different groups? We originally didn't test them in groups, and what we've found in recent years, especially with dissimilar engines and dissimilar alternators, larger, smaller machines in parallel with one another, when they are asked to either take a big load or reject a big load, sometimes they can become unstable, and then the system may fail just for the fact that the big machine steals all the energy, the little machine goes out on reverse power, suddenly you haven't got as many generators on the line, the whole system falls over. So there's a lot of sensible testing that needs to be thought about. We still haven't even got to put the wind turbines on yet. Active kilowatt and kVAR sharing these days are pretty standard in the controllers that you can buy, and without that you're making energy, well, with the VARs especially, you might be making energy in one machine and feeding it to the other and just heating up all the cables and burning fuel. So that's pretty standard now with the controls that you can buy for the gen sets. Do they have it? If not, is it worth installing? Probably is. There's a fuel saving just going down that road. So that's all in line with upgrading their control system. Protection systems are always entertaining. Everybody has a different way of setting them up and different preferences of how they should work. Different standards they need to apply in their location, whether it's some sort of regulatory body telling you how long the system's allowed to run at a lower frequency than rated, or voltage, etc. How the feeders are going to trip out. Do they have feeder load shedding in the event that the power station's starting to struggle, maybe low frequency, low voltage? And especially when you come along with your big wind turbine or your renewable resource and bolt it on the side, which was never intended in the first place, will you start tripping out feeders or start tripping protection because you're making energy from different locations? So that's a whole study in itself, is to review the protection that's existing and put in a plan to install something that's going to work with your new design system, integrating the renewables. Like I said earlier, then there's those other limitations that are applied that are not the fault of the power station. The owner, operator, regulator, utility may enforce a rule that says all of our power stations must run enough engines to carry the load, plus a spare one or two. We've had customers that want to carry 2 spare engines spinning online, just in case 2 should fail. So how are we ever going to save fuel, is what we usually think to ourselves. We probably don't say it to them. Then, you know, you have to go through that whole discussion and say, oh, okay, so your generators are really, really unreliable then. No, they generally don't fail. Okay, maybe we take one of those ones off and see some fuel savings. Oh no, that'd be against our internal requirements and rules, and we only work here for 40 years, so we can't change those. You know, there's all those things that are applied, and sometimes they may or may not be able to be changed. The client, the grid, the utility that's selling the electricity may have expectations or demands on the power station. Whatever the power station might mean, whether it's the diesel, the wind, the solar, whatever you're pushing in, maybe you have to behave in a certain way. Maybe you're not ever allowed to go within plus or minus 2 hertz, 1 hertz, 10 hertz, whatever it is at your location. Maybe they need a certain amount of inertia online to trip for faults if and when they occur. We have a client that is very much the opposite to the example I just gave, where they are super happy to run only the right engine for the load, and they really are keen to save fuel, which is good. And then when the renewables came along, they're like, oh, that's great, we'll do that too, and we'll run the gauntlet. Sometimes there might be certain scenarios that if the whole wind farm was to trip out, well then we will have to have a blackout. We don't want to go with storage yet, but we'll do that. That's really great. And eventually what happened is one of the distribution power lines came down in a storm, or didn't come down, fell off the insulator on the power line onto the steel pole in this location, and there wasn't enough protection and inertia on the system to trip that feeder. And in fact, what the control system did is said, oh, gee, the load went up. So it started up more engines and started feeding this huge load that was going down the pole and into the ground. We worked out that was probably about a month before it was reported, because we saw the load go through the roof and the fuel figures went through the roof. Now that we're looking at the problem, once we had it reported and found out what it was. And what happened was the people who lived in the community, the Aboriginal people from Australia, Indigenous people, they're very nervous around electricity. They're really great clients. They never dabble with the wires. They never come to the power station and muck around, because you know they're very aware that they could get hurt, and they don't go near it. And what they were saying, it come back to us through a long channel of Chinese whispers, that there was this evil power pole. There was an evil power pole out there somewhere, and the adults couldn't go near it, but the kids could. Okay, better go and have a look. So we went and had a look, and sure enough, it was evil. You couldn't get near it because you were getting electric shocks walking towards it. So you're probably starting to understand where I'm going with this. The step voltage between your 2 feet as a child, your feet only take small steps, and the step potential between your 2 feet wasn't so great, so the kids could walk past this pole. Luckily, no one had ever touched the pole, but the adults taking larger steps were feeling a sensation, or not. So it became evil. So yeah, they took and as soon as someone went out there and had a look at it, they looked up and sure enough, here's the transmission line sitting on the pole, steel pole, just sitting there, having a great time. And the power station's working flat out. So, you know, that whole fault ride-through requirement to be able to trip feeders, make sure that the protection works, that they've got either high-speed tripping mechanisms, circuit breakers, fuses, whatever it is, it's very real. Essentially, that is something we come up against when we really want to go high penetration and potentially diesel off. We actually hit that problem of not being able to feed faults should they occur. So that's been something that we as a company has had to work hard on. How do you do that? If you're not running spinning inertia, if you're not running an alternator, copper alternator, pouring inertia down the power line, how are you going to feed that current into the system to trip the breakers? I think, no, I won't even try and guess what normal alternators can feed. I think it's 6 times their rated current for a second or two to be able to help you trip breakers. Whereas if you're using inverter-based technology to provide the magic box that's holding the system together in a diesel off situation, a lot of inverters can't feed that sort of fault current into a system to trip breakers. So the system either goes really brown and sits at a much lower voltage and sort of struggles on, or it actually gears up and brings more generators on and really pushes power down the line and may or may not trip the breakers. So yeah, that's a limitation that needs to be understood and considered and taken seriously. Okay, lots of talking from me, not much from you guys. Oh, there's someone.
How do you fix that throttle?
That's a good question.
Condenser.
Yeah, absolutely. That's a spinning mass. So yeah, synchronous condenser or synchronous complicator, where you can spin an alternator with an electric motor, is certainly a method of doing it. It's quite efficient, and it provides that fault current. So you'll see that. I believe there's some in Alaska. There's systems that have got those installed. Is that? Yeah, we've got that. Yeah. So that's a way of doing it, of still spinning a mass using an electric motor rather than diesel motor. There are inverter-based solutions that can fix it or have a good go at fixing it as well, but they are limited. So everything's limited. You just need to understand the limitations of this device are X. Therefore, I can feed a fault current of XX or triple X or 6Xs, whatever it is, and that needs to be put in the protection plan to see if that's acceptable or not. It's quite complicated, and it's probably above my knowledge of power electronics. So I can talk to you later about the machine we do. You can do 6 times its rated current for 1.5 seconds. So if that protection is fast enough to operate in that time, then that's good times. But if they may have a sequence of events that needs to happen to trip feeders off after 1 second, another one after 2 seconds, etc., to try and keep the town on, then that may not be appropriate technology to use, and synchronous compensator are much smarter. Robert?
The other possibility is monitoring and modelling the system so that you detect it, but then you're depending on the controls.
Yeah, absolutely. That's for sure. You need to monitor and identify the fault and localise it and try and just trip its area. The trick I think we're talking about is what are you using to trip it with? If you're running diesel off, for example, and the nice big alternators are not spinning anymore, the energy might be coming from inverters, from a wind turbine or a solar array, or hydro is not such a big problem because it's usually spinning a conventional alternator. Then you may have fault current issues. You may not be able to feed enough fault current to trip the protection or trip the breaker or blow the fuse, whatever it is. So it's a challenging one that we've struck a few times, and we've had to model that in advance of going to the site and actually implementing what we're trying to do with the upgrade. It's a real one to look out for, because the last thing you want to do is build something that could potentially allow the power to stay on in some form or fashion, even though there's a fault on the line, like that example I gave. So it's a hard one, probably something that I'm not well enough versed in to talk too much more about, but I'm aware that it's something that we do spend a lot of time. We've got guys there that have to model that, like you say, in the beginning, and work out what the fault current capacity of every device is on the network. Therefore, when we switch around to this configuration, we've only got this much fault current capacity to feed into the grid. Should there be a fault, is that enough? No, well then we can't run that configuration. We need to run one more engine or something to that effect, a synchronous compensator, a few other magic boxes out there. So yeah, the modelling has become super important and super helpful and quite cheap. In the past, 10, 15 years ago, people would build things and hope they worked, or believe they might work, or it should work. We sat around and drew some pictures, not probably using a computer that much in those days. That should work. We'll put some wind turbines in and we'll bolt it all together. These days, with these computer-aided modelling packages, energy flow, dynamic modelling. There's a lot of money can be saved in building a system that's destined not to work, or needs to work in such a limited capacity that it's never going to pay for itself, or it needs to, you put in a 500 kilowatt machine that's only allowed, can never be allowed to run at 100 kilowatts because of this sort of fundamental philosophy that was overlooked. Peter?
I'm getting back to your scenario with the Eagle Tower, and I'm missing something. I'm not a power engineer, but it seems to me if you've got this fault and it's still there,
Yeah.
and all these other generators are going out of the system, are gearing up to compensate for the depressed voltage, but they'll never succeed in the voltage will just stay depressed, right?
Yeah, well that's what we all thought. It was a high voltage transmission line, 11 kV, 11,000 volts, and we went back to the protection engineers and said, surely once we got 3 or 4 generators running, we had enough inertia to trip the protection you had. And they said, well, interestingly enough, there wasn't that much monitoring equipment on site, so no one really knew why it didn't trip. There was no high-speed graphs trending this, but it seemed that the trip mechanism, the trip protection relays they have there are quite basic, and they said that it would seem that the voltage would dip and then raise and dip and raise as the cable was sort of chewing out the steel, and it was getting to a point where it was sitting there touching the steel, not touching the steel every couple of seconds, and it wasn't long enough for the protection relays to ever trip. It just seemed to be one of those scenarios where, you know, it's like it knew that the protection timers were there.
Yeah, high resistance ground driving
So then there was enough resistance in the ground.
Yeah.
it. You
Oh yeah, we
can't
we don't have very good resistance.
Huh.
Yeah.
That's
We
a great
often-
story.
Yeah. We often have to run a lot of copper in the ground to earth our transformers. It's up to 500 metres, so
You get high ground resistance from across.
Oh.
Out there comes from.
yeah. With the permafrost, it's not very well insulated. Do they run aerial earths generally for that reason? Or
Sorry?
would you run an aerial earth around the system to?
Well, you know, you just need to know what the ground resistance is. If you're putting in a substation and you have some options where you put it, you want to put it where ground resistance is lower, and so
Yeah.
you get higher fault currents. Or sometimes you have to, you know, run a ground grid to get the resistance low enough.
Yeah, it's. I'm led to believe it's more common than
Or
we would
you know,
think.
put in wells, drill holes.
Yeah.
I've forgotten the terminology.
Special dirt. Yeah, yeah. We've had to do that. We'll hear about it. The solar project we did last year, where it was just rock, and the rock, the resistivity in the rock didn't exist. So we had explosives blowing the rock to bits everywhere, trying to get our earth grid down. That didn't work. So what we ended up doing is putting an earth grid on top of the rock. That's beautiful. There's a nice big earth grid, and we came along and had a civil construction company build up the soil, and then we built the power station up there. So the whole power station was about that much higher than it should have been, because we couldn't go down and find a good earth. We had to raise up, create a good earth, and then run aerial earths around the community to make sure we're all talking the same earth potential. So that was a super big costly variation for the client. And I think the civil contractor bought a few new tractors out of that job. So yeah, this computer modelling is quite powerful and very helpful for the maybe it's the engineers or the guys that are coming up with the concept in the early days. What is it? What are we going to do? How are we going to do it? And these days, there's usually levels of convincing, I guess, that need to take place. And if without this model that you can go to the client, and these days the tools are quite impressive and quite user-friendly, and even a lame sort of electrical engineer type person can look at the tool and understand the numbers that are being put in front of them, saying, this tool, I've fed in our data, this is our power station, I want to put the wind turbine in, I've monitored, I've done all those tests that I talked about earlier, I've got all this great data, I've pushed it into the tool, and it's telling me that we can put in 2 wind turbines and it's going to be a good thing. Okay, well, we've got a budget for 3. That's rarely what they would say. Well, we can't do 3 for these reasons, and it doesn't make sense to do 3 for these reasons. Or yeah, if we can do 3, great, but these would be the things we'd have to do to ensure that the system holds together. Because at the end of the day, we need a reliable system. So these models can be done within a computer. You know, a consultant usually would do them, or someone would. And I believe Homer's a tool that's out there. Peter will talk about later. That's one of the tools that you can use. You can do a lot of the work yourself. The more knowledgeable you are about how the system works, how much data you can put in it, the better tool. I guess rubbish in equals rubbish out. If you can put better data into it, you'll get a better solution out. Then it can be verified with the actual data that you can then see taking place on site if this power station is an existing power station. And then you can prove to yourself that you're gaining confidence that what you're proposing, what you thought might be a good idea because you had a big flat hill over there with wind on it, might actually be a good idea once you've pushed the data through. There's a whole financial calculation that should really take place. Someone's going to have to pay for this. Someone's going to want you to give them some sort of presentation to say, you know, I need X $1 million or X $100,000 to do this project. I believe it's a good idea, and here's my substantiating evidence using these tools. There's a whole stability modelling programs out there now that'll actually give you predictions on how the voltage and frequency will behave in that system when you run these different scenarios, when the wind is high, when the diesels are low, and a power line falls off a pole. All that is modelled. Look, it says here that we won't lose the whole town, it won't black out, or yes, we will lose feeder C, but that's acceptable because I don't live there. I don't know. All that conversation can take place in advance. And then ultimately, whether or not it's a bankable project, that may or may not be a scenario that's important. But generally, someone needs to know whether or not they're really wasting a lot of money or they believe it's going to be a good solution, both with social and commercial or economic benefits for the community. So, a bit of a basic sketch, but data gets pushed into a computer. Computer does magic things and pushes out graphs that would otherwise be what you'd expect to see had you had a real power station in the place of the computer. So you can, if you're only looking at the diesels at this point, you can actually verify your data and say, okay, I've got all the raw data, I pushed it through, and these predictions are being made. Go back to the power station, try and simulate such an event. Is it true? Oh no, it's not, because I didn't set up a parameter in here properly. So until you get that right, you don't have something that's real to work with. And then all the different control algorithms can also be modelled depending on how the control system works. So if you've got the ability to get inside the control system that's there and understand how it behaves, you can actually model all that behaviour as well, so that you really do have a verified model of what it is you're trying to do, or what it is that's already there, and how the control system that you're proposing will work with the new renewable resource that you're hoping to put in. The more effort you put into these models, the better the model becomes, the more reliable it is. And it's something that's actually an asset to the client at the end. It's not something that you only needed to get over a certain stage and you throw it in the rubbish bin. It's something that they can then put to the side and use again later. They might want to build a new, I noticed in Alaska they were building those big community centres, you know, huge big indoor building with maybe an indoor basketball court, a heated facility, fantastic building for the community. But you know, the impact that will have on the electric grid could be quite substantial. So you can pull your model back out again and say, okay, all right, we need to now change the numbers. That feed has gone from 100 kilowatts to 450 kilowatts. It's got a huge resistive component, very little inductive, and you can push all that through again and can say, oh, gee whiz, that's going to cause this problem over here that we never had before that building was, or that large change to the grid was going to be installed. And you could install, whilst the construction guys are building the building, you could be over here doing the magic fix that's going to keep the power station together, rather than find out when they turn the building on that something else has gone wrong. So it's an asset, becomes an asset to the client, and I think it's quite valuable. We've certainly sort of bought into the whole idea of doing the modelling. and it's quite cheap in comparison. You pay a consultant or somebody to do modelling, you know, much smaller amounts of money than you would pay for someone to build your wind turbine to find out it doesn't work. Generally, you know, what are you going to do with it if it's not the right product for your location, or it's not, there's not enough wind, for example. You can model the wind, and you find there's not enough wind there, that was a waste of time. Then the next step that can generally take place is you can in fact test the hardware, whatever it is, whatever platform, PLC, industrial PC, whatever the controller is you're going to use, you can integrate that in with the model and watch it behave and ask it to carry out its functions and feed them back to you, so that you can test the hardware and the delay times within that hardware and bring it back to your little model that's pretending to be the rest of the power station, and do the real test without having to go buy all the diesel generators and all the wind turbines and all that. That's a bit further down the road. You're starting to buy better hardware, but it's still certainly not as far as having spent millions on a whole new system that turns out to be the wrong type of system for the site you've got. It's quite neat. Here's another Homer page. It's one of my favourites. You get other results such as this one. Now, this one is showing, let me get this right. It's showing the price of fuel, what the price of fuel would have to be versus the wind speed, tells you what type of technology you should consider for this site. Now, often up here it's a foregone conclusion that it might just be wind, that's that. In Australia it's not quite so black and white. Our wind is often marginal, or even solar is often not so good. If it's a lower, in Australia they have cloud, lower solar radiation levels, shorter days for example. So you feed all that data in, you let it know the site, you let it know your wind speeds and your solar radiation, all that data into Homer, and it gives you this great graph. Now I apologise for the metric numbers in here, but essentially, say for example here, at 4 metres per second, don't know how that converts to miles per hour, not that windy. Sorry? 8 knots. 8 knots, there we go. Are you talking knots for wind speed up here?
No, we talk meters per second.
Oh, you're metres per second. Oh, great. We're on the same language. I don't think you talk litres though, so we'll convert that side up. But at 4 metres per second, this is essentially saying if the price of diesel stays below 60 cents per litre, so what's that, about $2.40 a gallon, just burn diesel. You know, that's okay. It's probably not that okay. It's not that good for the environment. The green people wouldn't be that excited. But it's the best business case with the data you've pushed in. That's what the client should seriously consider. Then as the price of diesel goes up above this line here, it's starting to look good for PV diesel based on the data that was installed in the model. Likewise, as the wind speed goes up, there's a hybrid system here where it's semi-solar and wind, and over here is wind world, and it just goes forever. The more wind you've got until you get to a point where the machine's shut down, I suppose, on overspeed. But it's quite interesting and quite visual for non-engineering type people. You put this sort of table in front of them, you explain the two axes, and they go, oh, that's cool. Yeah, I'll put my finger there, that means that, and what is our wind speed? And you tell them that it's 6, sir. Oh, 6. Oh, that's great. Oh, well, that's a no-brainer. We'll definitely give you $3 million. So, you know, that's the sort of, oh, here we go.
It looks like all of them there you have included a battery.
Yeah.
And just any comments on that? Because I mean, there are times obviously when batteries are at least expensive.
Absolutely. This is unfortunately, at about 2 AM last night, when I pulled this down from our server, I couldn't find the one I really wanted to find. This site, the battery solution isn't necessarily just needed in the diesel world, and not necessarily needed in the wind side either. So, in this case, it's indicative of the graph that you would see. I mean, Peter, maybe you can comment. It's up, like I said, rubbish in, rubbish out. If you provide poor data, then you'll get poor results.
Yeah, actually, this is a very small site.
Yeah.
So in smaller systems, store batteries are easier to deal with. So larger systems, you have different.
I mean, not to get get too complicated, I could imagine, you know, every one of those with and without batteries, right?
Yeah.
So you could have diesel with
Yeah,
batteries,
for
you
sure.
could have 8 instead of
And we're talking energy
4.
flow.
Yeah.
So yeah, absolutely. You certainly don't need batteries to supplement the diesels. You may or may not need them with the solar. It just depends on the penetration levels. It's more of a, I think it's a dollars thing to get the client thinking, how much money does the fuel have to go to before this starts to make sense? But it's quite a good one to get them on board with what you're trying to say to them, what you're trying to say. Look, I've looked into this. Yeah, I do apologise for the battery confusion I put in there.
No problem. I mean, it's just actually though, because batteries are a big issue in a lot of these
Yeah.
situations. Do you want them or not? And
Yeah.
so actually modeling this, a lot of times your first question is diesel or diesel and batteries, and
Yeah.
then you get into the renewable option. Right?
Absolutely. The base case that we're always comparing to is diesel.
Yeah.
And we have an expression where we say that if you do confuse the client, like we said at the start, then it's just so easy just to say no and just not get involved, and we'll just keep burning diesel, irrespective of where the wind regime may be or the price of fuel. So the battery argument is also modelled inside Homer, the costs of maintenance and the periods that you need to do these sort of things in. So it's quite good, and that would push the graph around. The more data you can push in, the better the graph becomes, more accurate. And it's an energy flow calculation, so it may or may not be dynamically sensible. There needs to be a level of sensibility applied when you do run these models. You need to sort of go, okay, is that really the case? Could I really run the whole town on 50 kilowatts of batteries? You know, it's not going to spit out bad results. It's going to spit out results for you to consider and say, okay, have I fed it enough information to give it a chance to calculate that correctly? So it's a good one though to bring along people who don't have a good understanding or don't really get what you're trying to say. There's a small number of wind turbines being installed, so you're pretty much seeing the gusts come through the wind farm pretty quickly. I know at Kotzebue they've got a lot of smaller wind turbines, but the effect that the wind farm would have, I suppose if they were all 200 or 300 kilowatt machines, then they might see predictions come through the wind farm. They introduce all sorts of fun things on the grid. They've got the great capabilities of just turning themselves off to protect themselves like a diesel engine. You don't get any warning, of course, like you wouldn't with a diesel engine, so that's okay. They have characteristics or parameters that say we will work inside of these frequency and voltage limits and they're the ones generally causing the problems to the frequency and the voltage. If they go outside the frequency and the voltage, we're out of here. See you later. Fix that problem, will you, and we'll come back later. Which is all well and good on a large grid like Anchorage or lower 48, but on a small wind diesel grid, it's quite an interesting ride. We've seen them go from 100% output to 0% in less than 2 seconds and then come back again 2 seconds later or quicker. That's pretty nasty to the diesel power station. Once again, the consumers don't want to see that in their power. They don't want to see lights getting brighter and duller. They just want to see constant energy. So you need to be doing something that's going to tolerate these systems. And maybe not. Maybe the system is so small that the client is prepared to tolerate a little bit of voltage flicker or a bit of frequency diversion. Just depends what the client wants to do. If the client is strictly regulated by some external regulator that's dictating really strict terms, then this comes into play. We've even worked with these machines. I've actually got a couple of pictures of them. They're a French machine made in France. We put them up in Australia. That wasn't the problem. Where they're an induction machine, and I believe there's induction machines up here, where given enough wind, the machine will put in up to 150% of its rated output for a little while until it pitches its blades or pitches itself. And on top of that, it's also got a gearbox, so halfway through the power range it just turns itself off, changes gears and keeps going, which is pretty cool. Except if you're the diesel power station that suddenly has to pick up all the energy while it just changes gears over here and then goes back on. So they are pretty wild machines to work with. But in Australia, in this location, it's a cyclone location or tornado location. Conventional wind turbines wouldn't be allowed to be installed there. the manufacturers wouldn't let you. So these machines were great. They tilled up and down clearly, and they gave wind power to the location for the other 11 months of the year when there are no cyclones around. This one here, we worked really hard and mounted it on top of the car. So, how much wind can you put in? I remember for those of you that were in Ottawa 2 years ago at this conference, there was quite an interesting side debate that started to happen between the speakers where everyone started to talk about this thing called penetration. It was G-rated conversation, let me tell you. Yeah, someone was there, yeah. So we have this funny lingo. Actually, I think one of the talks was completely based on this topic, that this industry, wind diesel group of people that grew from probably half a dozen guys to a couple of hundred people now, came up with this great terminology called percentage penetration. And from those on the outside, I think one of the speakers got up and said whenever he talks about it to his wife, she's like, what are you talking about? I don't want to think about what you're talking about. So we've stuck with it. We've added the word instantaneous in front of it for now at our company because we can't think of a better term. We're all ears in case you guys have come up with a better term, and we'll certainly convert. But how much wind to put in, how much instantaneous penetration of energy from the renewable resource can be put into the grid is the question that we're trying to do. So from our company's point of view, we would say that you can go along, if your instantaneous load doesn't go below, say, 100 kilowatts, you could go and put in a 30 kilowatt machine, 40 kilowatt machine, and the existing power station would just work. The automatic governing on the diesel engines or the electronic fuel injection on the diesel engines will be quick enough, as a rule of thumb, line in the sand, that it'll be able to pick up that 30% load fluctuation, plus or minus, that's going to take place when that wind turbine kicks in and out on the grid. So that's a general rule of thumb. It may or may not work in all cases. You might be able to actually put a bit larger percentage in. So that's what we're saying. A low penetration from our point of view would be in the order of 30%, up to 30% wind penetration instantaneous, which means the governors can pick up the problems. And then, like I said, we've based that sort of statement on using electronic fuel injected engines these days that are quite quick. That said, the spinning reserve would have to be set in the diesel power station to allow for that wind to come back at any time. The power station would have to be fully aware that the wind turbine could fail and I'll have to pick it up. And that's fine. So yeah, as such, fuel savings in such a system are certainly there. If it's a windy day and it's constant wind, you will save 20, 30% of your fuel bill. That's great. That said, you're probably spinning an engine anyway big enough to make the power, so maybe the fuel reduction is not as high as that. But it's certainly a fuel saving, there's no doubt about it. It would work fine. And you'd only have that capital cost of the renewable and none of this fancy integration that I'm about to talk about, or storage and stability. So there's a couple of different solutions that are out there. I think there's about 200 more options. Yeah. There's companies that will provide compressed air solutions to you. There's hydrogen type solutions for demand side management, steam solutions. In Australia, there's a company that's built a carbon block that you push excess energy into in the form of heat, and it's very efficient at storing that heat, and then later on, when you need the energy, you can get it back out, convert it to steam, away you go again. There's plenty of great storage technologies out there. Each of them have their pros and cons, I'm sure, so hence the confusion. This one here, I just wanted to use an analogy that we use for our guys, and this has come from a slide that we've talked about before, where you can imagine yourself driving along in a car that's got cruise control, so you don't have to put your foot on the throttle anymore. and you're going up and down a couple of hills. Now, small hills, you'd notice, and I think most cars probably come factory fitted with cruise control these days, I guess. Going up a small hill, the car can quite capably make its way up that hill and maintain the speed set point that you dialed into it. So the analogy that we'd make there would be that the frequency of the system would be fine, and the governors would just be given more throttle, more fuel would come in, and you just make it up the hill. That'd be great. Likewise, when you go slightly down that, up the back side of that nice gentle hill, the governors would back off, the speed setting would be maintained, and the police don't pull you over for speeding. That's great. The problem comes, I guess, is when you go up a steeper hill, and you know yourself, especially in an automatic transmission vehicle, as you go up a steeper hill, the revs, the vehicle can't maintain that speed, so the car switches down a gear and you can go up a bit quicker, and it maybe has to switch 2 gears, whatever it needs to do. And likewise, I noticed in a new car that I drove recently, going down a steep hill, that it actually, in cruise control, it actually pulled the gearbox in to a lower gear to pull it up so that the speed didn't run away, which I thought was different for me. I hadn't experienced that in an older car that had cruise control and automatic transmission. Usually, if you weren't watching, your speed could go up and up and up and up. So that we would liken that to the case where the diesel engines can't quickly pick up that load. So that might be the wind turbines have suddenly just disappeared. The wind's dropped off quite substantially. Therefore, the load's going up and up and up. The diesels aren't able to pick that up and meanwhile maintain that frequency, so they may have to start another engine, and that would be the same as that gearbox scenario. Bring another engine on, get going. Likewise, you might bring on some of this magic storage stability stuff that we're going to talk about to assist the diesels to get up the hill. And then on the other side, where suddenly the wind turbines come back and steal all the energy back off you, you're stuck carrying all this excess capacity, and over a generation, it could well be the case that the storage would then take some of that capacity or that generation from you and recharge itself in the form of that switching down the gearbox to stop you from overspeeding. And that's where that analogy sort of comes in. When you talk to people, and I've tried this one on my wife and she sort of got it, that people who aren't in the industry, what are you talking about when you talk about this storage component? And what are you trying to say? Well, you watch the car when we go up this hill and down the hill, and she's like, don't do that, the kids are in the car. Like, I'm trying to tell you this thing, concentrate. So, we try and go, that's what the system's trying to do, using this storage and stability devices to assist it to maintain this stable frequency, to assist us to live here as the consumers and not know all the problems that the power station's experiencing with the gusts in the wind or equipment tripping out. So this website here, electricitystorage.org, is a very good website to give you more information about all the different types of storage. This is a cut from their front page. It's really quite well explained from my point of view. The power quality is applied for a couple of seconds. That's that stability type of storage I'm talking about. You hear people say, oh, okay, you've got a flywheel. They would say to us, you've got a flywheel. What sort of energy storage is that? Well, we're almost trying to say that it's, from our point of view, the type of flywheel we're using, it's really not storage. It's such a short amount of time that you wouldn't be that excited about buying a battery that only lasts for 18 seconds, which is the flywheel that we run. It's 18 megawatt seconds of capacity. So this whole stability / quality tool is well described there. Then they talk about bridging power as being a device that might be there in the period between seconds and minutes. So it helps you maybe start another generator up or get through a lull in the wind until the wind comes back. You didn't have to start another generator. Or likewise, if the sun went behind a cloud, and that sort of thing. So, and then of course there's the longer term storage, which is the holy grail. There's big battery companies out there now that are really becoming attractive and doing some great things where you can shift energy from this morning when it was windy, we had too much wind, we couldn't consume it all, and let's put it in later. when the wind drops off. So once again, the same websites. I won't spend too much time stealing their slides from them, but it's quite interesting. You can see the different characteristics of energy versus time of the generally speaking, the different types of technologies that are out there. And I'm sure that, for example, Beacon Power here from the flywheel green coloured circle there, they're sort of stretching this circle in a different shape now, the way their flywheels since advanced since 2008. But these different types of batteries, I'm sure they've changed a little bit, but it's a good indicative graph to say, okay, so if I need a megawatt, I can get this type of device here, which is capacitors, for about, what's that, 10 seconds, up to about 10 seconds. Great, that fixes my solution, that's what I'm going to buy, away we go. Pumped hydro, of course, is great, heaps of energy for long periods of time. It's out there on its own generally. But all these other types of storage devices have all got their place in the sun. A couple of them overlap, and they've all got their pros and cons. So I guess that's what I'm trying to demonstrate there. And Kat's telling me to hurry up, which you'll be happy about. Okay, so yeah, that being the case, these high penetration type systems that you can then go for would be able to supply up to 100% of the capacity or the instantaneous load. At the previous conferences, there's people that talk about greater than 100%. I struggle with that and get confused, so I'm just going to leave that there and let other people explain that to us if it comes up this week. Annual fuel savings is really what we should be talking about. Instantaneous is all well and good, and it's really exciting to watch it here and now, but the annual fuel savings is what the community really cares about at the end of the day, because that's their fuel bill over a year going down. So we've seen an average of 50% in annual fuel savings in sites where the wind made sense, and in Antarctica we've seen sites where the fuel savings are in the order of 80%. So that is good. Long-term storage, our company hasn't installed a system with long-term storage to date. We're watching the space, we're really interested and keen to watch the technology improve and continually trying to test the business case to see if there's a positive return, or if it's close to becoming a positive return, if the technology is mature enough. It's one of the sites we did that was high penetration. I will start to speed things up. I've said to Kat this morning I was worried about not being able to talk long enough. Clearly that wasn't a problem. From there, so we've built this great system. We've done the diesel, we've done the wind. We're really happy we're doing these great things. Future type things you could do just to make a few more improvements would be demand side management. It's been done by many people wide and large. The interesting thing is that the communications that are now available to us with wireless technology and super fast Ethernet and internet and all these different types of communications, that used with our technology back at the power station, we can switch things on and off at the millisecond rate. We can turn off people's air conditioners in Australia, maybe it's heating in Alaska and Canada, for 5 seconds, while, because we just lost a diesel generator, we've got to quickly get another one going, or the wind just dropped off. They won't even notice because they gave us permission 2 years ago to do this. So in their room, the heating goes off for a few moments or even a minute or so while we get the power sorted back out again through some sort of wireless communication, both monitoring and control. That's where we can see another few percent of fuel savings there for very little cost and infrastructure these days. So we're pretty excited about that stuff. And likewise, electric cars, plugging them in at night time to charge. I guess it's coming. We're seeing it coming. Why not use that battery as inertia on the grid, providing extra energy to the grid if and when you might have needed it. So that's something there worth looking at. I might skip, how long have we got? Okay. 1 minute, all right. Okay, what I'll do is I'll skip this video for something that's old. I can show it later, we'll put it on our booth or something. But I will see if I can flick to the, there we go. Why are we doing this? This is the oil price over these years. last night it was $106 a barrel, so it's sort of up here. It seems to be the case that once oil goes above $80 a barrel, wind makes sense. Once oil goes above $100 a barrel, solar starts to make sense as well. If you don't have a wind resource, then that's the sort of business case numbers that are nice rules of thumb to use. And now we're at 106, and who knows where it's going to go next. We saw it go right up here in 2008. So that's why we're here. That's why this industry exists, because of the drivers. How do we go forward from here? If we're here, do we believe that there's a high oil price coming? Probably. Should we stick in renewables? Well, we don't have to, but it's possibly a good idea. So what we could do is wait until the high oil price comes and then put the renewables in, or we could encourage people to actually do it sooner and be ready for the high oil price. So that's the stimulation that we're trying to do in conversation with clients and potential people who are thinking about doing this. I'll quickly flick my screen over and see what this thing is doing. So, amazingly enough, it looks like it's still working. Although it's stretched out in a funny kind of way on my screen. If there's any computer experts in the screen to teach me how to make that better. This is a power station in Antarctica. It's actually 2 power stations in Antarctica. The Americans have a research station down there at Ross Island. Very large, because that's how Americans do things, very large. Big diesel engines, and that's cool. It's really cool going to a power station with big engines. And just over the hill, 3 kilometres away, was a little New Zealander power station with little engines. And they're running at 50 hertz, and the Americans are running 60 hertz. And 3 kilometres apart from one another, the Americans built a runway 50 years ago. They've been flying their little New Zealand friends in for 50 years for free, being their buddies, bringing their big cat loaders over, helping out the New Zealanders while they putt around in their little 4-cylinder cars. It's really sort of cute, big brother looking after little guy. Anyway, a tender went out worldwide to see if these 2 power systems can be joined together. The New Zealanders paid for it. The New Zealanders wanted to help say thank you to the Americans and also go green. So they threw in 3 wind turbines, Enercon E33s, 330 kilowatt machines. And as luck would have it, they're flat out right now. This is the site that I was telling you that they get annual average fuel savings of 80% because the wind turbines just don't stop. I don't know if I can scroll down. That's the data down the bottom here. So yeah, stage 1 was to bolt the 2 systems together, put a frequency converter in, so it's 60 hertz all the way along here up to this point, gets converted to 50 hertz, and then the little New Zealand base, which only has up to 60 people at maximum capacity, the American base can have up to 1,200 people, has little electrical lights and things going on. So, great project, super interesting, amazing location. Stage 1 was to put in these 3 wind turbines and a flywheel-based system to ensure that the grid was stable. Generally it is stable because the Americans have such big engines, but at this current system load of, apologise for the resolution. So the current load is 1,700 kilowatts right now. They're running a 1,400 kilowatt machine and 330 kilowatt wind turbines, and the flywheel there's that machine I spoke about earlier, 18 megawatt seconds. It's a 500 kilowatt flywheel with a 500 kilowatt front end, I should say, on an 18 megawatt second flywheel. So they've got about 500 kilowatts for about 45 seconds of storage there, if you like. So if these wind turbines all fell over instantaneously, they'd lose 900 kilowatts, 500 of which would be picked up by the wind turbine, 400 of which would be picked up by the diesel. The lights wouldn't go out. If the wind didn't come back in a period of time, then they'd start up maybe one of these guys or one of those to keep the lights going. That's how it currently works. It's in a state of assessment at the moment. It's been running for a bit over a year. You can see here the wind speed, 14 metres per second. That's great. Stage 2 is to put in 13 more wind turbines and 5 more flywheels and electrify all the heating loads around the site. So that's cool. You know, that's where it's going to be at. They'll be able to go diesel off for long periods of time with that sort of system installed. They've got, they don't really know, but they've got an estimation of how much diesel heating load they're currently seeing, which we don't see obviously here because it's only electrical load. They've also got another electric diesel generator out in a shed because this power station burnt down a couple of years ago, so they're very scared of losing power stations. So this site is a really exciting wind diesel site for this industry, and you know it's in a World Heritage area. They're trying to reduce their carbon footprint as well as the amount of diesel and pollution they're causing down there. And it's what we're all trying to do. This is this wind diesel thing we've been talking about. Yeah, it's big, but it's the same as doing it on a small scale. And it just goes to show it works. It can work. So I'll leave you with that. I apologise for talking the whole time. Is there any questions before Kat takes the floor? Great.